branches. So let's remember from yesterday, we saw the crucial ratio lemma, where we saw the statement of it. Let's remember what it said. So the crucial ratio lemma said that if I look at the probability that the random graph has some degree sequence d, and I compare it to the probability that it has some nearby degree sequence d minus EA plus EB, so I have here my degree sequence d, say, and in coordinate A, I delete one, and in coordinate B, I add one, then that ratio can be approximated by that formula. And I call these two degree sequences adjacent. Just whenever I can form, like I can do this swap, I just call these two degree sequences adjacent. And we define this auxiliary graph S. And on dm, which was the set of typical degree sequences, we said that auxiliary graph has a small diameter. Small means like of the order of n times root d log n. And the point here is, I mean, whatever this formula is, the point here is that the error term that you get is little o of 1 over this diameter when d is not too large, okay? So the real thing what we want to do is we want to get a ratio formula for these adjacent sequences up to very small relative error, small enough so that it's little of 1 over the diameter. That's another reason why we want to like restrict ourselves to this dm, so that like actually like we have a chance of getting something small. Okay. Any questions for the statement? Okay, so that's the statement which we like, that's the heart of the whole argument. Like getting this error term really low. And that's what we will do today. And what I will define first is like an R, a B of D, and it might seem slightly counterintuitive, but I want to give it one argument, and I want to say that it's of this form. So this we will define to be, well, the probability that D of G and M is equal to D minus EA divided by the probability that the degree sequence is D minus EB. Okay, so just like an ordered tuple, at the top you decide you remove one from A, and at the bottom you decide you remove one from B. So this is of course only defined when this is what we call an odd sequence, meaning that the total degree is something odd, and then we delete something, it's even. That doesn't tell you that it's graphical, but let's just assume whenever we see a sequence for today, that it's a graphical sequence, and then like, so we can talk about probabilities. Okay, so with this definition, what we see here, that's an RBA of what degree sequence? I think it's a D plus EB. With this definition, okay? So I just don't want to think, yeah, like one reason why you want to write it like this is that formulae become nice and symmetric. Okay, but it's just a rewriting. So that's what we want to approximate, and when we want to approximate these two ratios, I mean, now I can forget about the normalizing as well. So that is just the number of graphs with degree sequence D minus EA over the number of graphs with degree sequence D minus EB. Okay? Good. So how do I get a good idea about the fraction or like the comparison of these two set sizes? I think you've seen this idea at least in Imre's lecture. You form an auxiliary bipartite graph on the set G of D minus EA and G of D minus EB. And so the elements, the vertices on this side are graphs G with degree sequence D minus EA. And then here I see graphs with G prime with degree sequence D minus EB. how do I form this auxiliary bipartite graph? When would I put an edge? And I indicated that yesterday. We put an edge there if in G you look at vertex A, you remove, like you take a neighbor, V of A, and you move it over to B. Okay? So pick any neighbor of vertex A. If you can flip this one over, meaning that this edge is not occupied, then you do it, and any graph you get, you connect this via an edge. So that's an auxiliary graph. And so what we want to do is estimate the number of edges in this auxiliary graph. So that's called, yeah, auxiliary bipartite graph B. Okay, so what can we say about the edges of this bipartite graph B? It's the sum, well, let me write on this side. The sum over all graphs G in G of D minus EA, the degree of this graph in this bipartite graph, in this bipartite auxiliary graph. And then, so that's counting the edges from this side, and then I just get exactly the same on the other side. So that's the sum over all G in G of D minus EB, the degree, or let's say G prime here, in B of G prime. And now, how would I know how many graphs, like in how many ways I can do this edge flip? Well, I write this as the size of G of A, D minus EA times the, that's getting, the expected degree of G in this bipartite graph. And this expectation is, I think, what Sarah also uses, is like just a normalized counting measure. So this is just 1 over this sum. So just G, pick G in G of D minus EA uniformly at random. Yeah, I mean, it's just an identity. And the same is true on this side. The size of G, D minus EB, times the expected degree in B of a random G prime. G prime is uniformly random in this set. Okay? So what is the expected degree if I pick a graph G uniformly at random? Questions? Well, let's say we pick a graph G in G of D minus EA. Let's pick it in G minus EB. All right, yeah. I think to go from here to here, I would have to go from vertex B to vertex A, but it's symmetric. Yes, so I pick a graph with degree sequence D minus A. I remove one vertex from vertex B, 1 degree count from vertex B. I move it to A, and I add 1 to A. So I get a graph that lands in this world. Okay, so let's pick a graph in G of D minus EA. And let's pick a random neighbor of V. When can I, like, move this over there? Well, I can move it over there almost all the times, but what are the bad events? So we pick G uniformly at random, and pick V, a neighbor of B in G, uniformly at random. So I can perform this flip unless, so the bad events are that my random neighbor that I picked was actually A, right? So then this would create a loop. So loop is like that A, B is actually an edge in my G and my random neighbor V is equal to B, right? Because, yeah. Then, so, yeah. Equal to A. Yes, yes, I'm flipping ABs now. Equal to A, yeah. So I look at my neighbors, I accidentally pick my neighbor A, and so I cannot flip it because this would create a loop. The second bad event is that I pick a neighbor which is also a neighbor of A, so that AV is also a neighbor, is also an edge in G, which then would create a double edge. Okay, so these are my two bad events. So now I can write out my expected degree of a random G, right? I know how many neighbors B has if I pick a graph here uniformly at random. In every such graph, like the vertex B has dB neighbors, yeah? So in total, I might have dB choices, but how many of them, like some of them might give me a bad choice. So let me just write this as 1 minus the bad probability if I flip from B to A. Yeah, B to A in this degree sequence minus EA. Okay, and that is, by definition, the probability of either L happening or D happening, and that probability is over the random choice over G in G of D minus EA uniformly at random, and V in the neighborhood of B uniformly at random. Okay, but like it's a different probability space than other probabilities. I just want to give this a name as a bad probability. Okay, so if I plug this into my double counting here, then what I get this is that the G of D minus EA times the expected degree here, which is the dB times 1 minus a bad probability from B to A of D minus EA is equal to what I see on the other side, G of D minus EB times DA and 1 minus bad, of AB of a D minus EB. Okay, why is that the same here? Because this flip, I mean, like to get the expected degree on this side, I can do exactly the same. I pick a random element in this space. I pick a random neighbor of A. I flip it back, and that gives me exactly the degree of this graph G prime in this auxiliary bipartite graph. So I just flip the indices A and B to get the expected degree on the other side. So that gets us our first recursive formula. So our first formula that we have established with this argument is that RAB of D, the definition is still here. So if I rearrange this, I think I get A dA over dB times 1 minus the bad probability when I flip from A to B in D minus EB. And I just divide by the indices switched. Okay. Right, so now, of course, we want to figure out what this bad probability is. Okay. So, so for this bad probability, well, we said it's the probability that I either have a loop event or a double edge event. So the claim is that bad, if I flip from A to B, and now I'm changing, I'm going to just D, oh yeah, let's keep it with E minus B. What is that equal to? I claim it's 1 over dA, that's for the random neighbor of A, times the probability that I see an edge between the vertices A and B in this degree sequence, plus, and for this plus I need to introduce, I need to introduce two notations for this claim. So let me write it. The sum over all V, which are not equal to A or B. And now I want to say the probability that I see both edges, AV and VB, and I will denote this by YAVB of D. Okay, so where PAB of D is the number of graphs in this degree sequence space where AB is an edge over all of them. So it's just the probability that I see an edge if I pick one such G uniformly at random. And similarly for this Y, AVB, that's the number of G in G of D, where I see both edges, AV and BV, and I divide by everything. Okay?
This YAVB should be of D or of D minus EB?
Oh, yeah, thank you. Yeah, the same. So yeah, that's why I thought I write it was, it's just the argument here is exactly the same here and here. Okay, why do we use Y? We don't want to use V because it looks like a V, but V is used for vertex sets. So yeah, Y was the closest. P is overused, so Y is just the next letter we came up with. It's a two-path probability. If you choose a graph G uniformly at random in your whichever set you are in. Okay. Okay. Why would that be true? So proof sketch. There are two things you need to notice. Well, the first is that these two events L and D, they are actually disjoint. Right, because if let's say I pick a graph uniformly at random here, and I pick a random neighbor, and I have this loop event, then that means that I picked V, my random neighbor was A, and I created a loop. But I cannot at the same time have that A and A is an edge, because that would be a loop in the original graph. So these are disjoint, that's observation 1. So I just add the probability that one happens, that L happens, and the probability that the double event happens. And now for the loop, that's the probability that I see an edge between AB, and I divide by the probability that that's exactly the neighbor I see. So this one is the probability of the loop. This one is a bit harder to see, and I put it on the example sheet, on the problem set sheet from yesterday. So show that the probability of loop, of the double edge, is equal to 1 over dA times the sum over all v not equal to AB of this y AVB. Yeah, I think I want to let you think about this for a bit, but if you want hints, let me know. Okay. Okay. Now, what we would like to say anything about our ratios is that we would like to get approximations for the edge probability and the two-path probability. So here let's just invoke a classical switching due to Brennan McKay. So a classical switching or simple switching is of the following form. So you pick a graph G where you have an edge between A and B, and you pick some arbitrary other edge, A prime, B prime, and you switch this edge between A and B away. You create a graph which looks like that. B prime, and so this is now not an edge anymore, and you stay in the same degree sequence space. Let's be a bit more precise. So that's a lemma that comes from this, as that the PAB of D is always at most the maximum degree of D. So the maximum possible element I see in my degree sequence D divided by dn times 1 plus big O of delta squared over dn. Okay, and the way you get that upper bound is the same idea that we used for the ratios. So you want to compare, before I say that, let's say, what is this edge probability? Well, by definition, no. Proof sketch anyways, but let's go back to that. So let me write V1 as the vertex set, the set of all G in G of D, where I see the edge AB, and V2 is the set of all G in G of D, where I do not see the edge. Okay, so here are my two sets, V1 and V2. And the point here is that the probability of AB is what? It's equal, well, the size of V1 divided, not divided by the size of V2, but almost. So V2 plus V1, which is just equal to the ratio over V2 times 1 plus the same ratio. Okay, but nevertheless, I want to compare V1 with V2. And I do this by that simple edge switching. So if I pick a graph in here, so it has degree sequence D, and it has the edge, I calculate in how many ways can I switch to a graph G prime where this is not an edge. So okay, so I want to estimate this degree here, and I'm only interested in upper bound, so I need just a rough estimate. So in how many ways can I perform a switching from this G to something where I don't see an edge? Well, it's the number of ways that I can pick another edge. Okay, let's so yeah, the expected degree of V in V1 is, well, let me just write the number of edges in this bipartite graph. So the number of edges in this auxiliary bipartite graph they are roughly equal to, well, the size of V1. So just pick an arbitrary G. And then how many ways can I perform a flip? Well, overall, there are D times N. Yes, I want to count. I'm given a graph G that has an edge here. In how many ways can I pick an A prime and a B prime so that I can perform that switch? Well, there are D times N on 2 other edges, but I can either do that switch this way around, or I might be able to do it this switch around. So in order to pick this A prime, B prime with an ordering, it's D times N. But I cannot pick an arbitrary edge because I do not want to create, I don't want to be that this is already an edge, right? So I don't want this edge to be like a neighbor of A. And similarly for B, I want to exclude everything that is a neighbor, an incident edge of a neighbor of B. So the total number of what I cannot do has size delta squared, right? A and B have size at most delta, and their neighbors have size, have degree at most delta. So what I cannot take for my A prime, B prime is at most a delta squared. But everything else is fine. Okay. And now I want to say, I want to count these number of edges from G prime. So of this auxiliary bipartite graph. So now I have a graph G prime where this is not an edge. So I do not see an edge here. And I want to say, well, in how many ways could I possibly have arrived here? Well, the way, like, if I arrive there, then I know this edge, like, was switched to some neighbor. And that edge was switched to some neighbor of B. So in this G prime, all I can do is pick some neighbor of A and some neighbor of B, and that's the best I can do. I might not be able to do any of those things if I'm like, I don't know, in a bipartite graph or something, but it's at most the size of V2 times delta squared. Okay, at most one here and one here. And if I equate these two things, then we get that V1 over V2 is at most delta squared over dn minus big O of delta squared over delta squared. Okay, and you plug this into here, and so this becomes a 1 plus big O of d delta squared over dn, and that is the same, and so that gives you this upper bound. So that's the simple switching, which has existed for many years, so that's not something new. But that gives us a good idea of, like, that gives us an initial way to plug this into this bad probability and that into that ratio. What I will say here is that a similar argument, with a similar argument, you can show that this YAVB is at most, let's say, big O of delta to the 4 over dn squared. Okay, like, I'm not going to do this because we will see something more precise shortly. But for this initial approximation, let's just say we can do a similar switching by switching away, I don't know, the AV or VB. Okay. Would. Any question? Yes?
So in your upper bound on the number of edges in this auxiliary graph, this delta squared could have been dA times dB. Is that right?
Kind of, but you also want to say something about the degree of the neighbor, and then you lose all kinds of information. So it's dA times, so it would be the maximum of dA dB times delta. Oh, wait, you are in this one. Yes, dA dB, yeah. No, for this one, it's not important. Yeah, right. Yeah, for the backward switching, right. You could just say dA times dB, but I think for the forward switching, you would anyway get some delta. And for us, for now, this is for first approximation. That's good enough. Yeah. Okay, so let's plug this into this and see what we get. Okay, so we have in dm, we have that all the degrees are concentrated. So we have that actually the delta of the degree sequence is at most 2 times the average, and that's a very crude upper bound. So in fact, in dm, we get that the PAV of some degree sequence is big O of d on n, and YAVB of d is big O of d squared over n squared.
This is PAB, presumably.
PAB? It doesn't matter, but yeah. Like you always fix your indices and you say for all distinct AB, yeah. So let's plug this into here. Then this gives that the bad probability of a D minus EB, where now I want this to be in DM. Well, it's the first one would give us a big of 1 on n, and I'm using here that this D, all the DAs are roughly D, plus, well, 1 over dA, the sum over all V's. And here I get a big O of d squared over n squared. And then, well, this is like the dominating term. So that will be also a big O of d over n. Okay? So we get that the bad probability, we can bound it by big O of d over n. And if d is sufficiently smaller than n, let's say this is little o of 1, then in fact, like, you don't need to worry about this 1 minus b to ever be close to 0 or something. Okay, so plug this into the ratio. So we get RAB of d to be dA over dB times something that's 1 plus big O of d over n. Okay, now d over n, remember we want a formula for the ratio that's accurate up to some very small relative error term. So what we wanted here is 1 over the diameter, which was 1 over n square root d log n. Okay, this will never be that small if d is at least 1. So d over n is never little o of this for any reasonable d. Okay? So that's not good enough. Okay. So instead of looking for some approximation of p and y, we find recursive relations for these completely combinatorial ideas and use that. So okay. now the lemma, and these are our recursive relations for PAV, and POY, YAVB. Okay, the first, I should say, yeah, let me write the conditions in a bit. So we have if A, let me switch to V because the V will come up. Like, yeah. A and V are in N and they are distinct. And then you have that the PAV of D is equal to dV times the sum over all B that's not equal to V, the ratio of BA of a slightly reduced sequence times 1 minus the edge probability BV of a reduced sequence D minus EB minus EV over 1 minus PAV of D minus EA minus EV raised to the minus 1. And the second one is that YAVB of a sequence D is equal to, that one looks a little bit simpler, the PAV of D, right? I mean, I want the probability that there is an edge between AV and an edge between VB. So I have the probability that I have an edge. And now what I see is basically the probability that VB is an edge, conditioning on that AV is an edge, which is equal to PBV of a reduced sequence, EA minus EV, minus the probability I have both edges in the same reduced sequence. And I divide by 1 minus the edge probability of AV in this reduced sequence. Okay. And the conditions are, I guess here you want AVB in N to be distinct. And the rest of the conditions, I'm not going to write them out exactly, but all that they make sure is that the D is graphical. Because if I want to talk about the probability of an edge in a graph drawn uniformly at random from all of these, I better make sure that I'm not talking about an empty probability space. Then I want these sequences to always be graphical. Same here. And I don't want that the denominator is 0. So the conditions are, the least you need is that D is graphical. And then some more that just make sure more, which says everything is well defined. Okay, but I do not want to worry about boundary cases at this point. We will show these recursions, just assuming that I always talk about non-empty sets for now. Okay. Now, let me for later. Oh, yeah, no. Let me just reduce. So we want to prove this lemma. And I promise you that it's a simple combinatorial lemma. Okay. What's at the heart of this is a very simple observation. The simple observation is the following. I need to, well, yeah, I will talk about numbers of graphs with an edge, with two edges, without. So let's write NAV of D as the size of all G in G of D, where AV is an edge, and similarly and AV and BV of D is similar. Right, I just have AV as an edge and BV as an edge. And here comes the simple observation. You can write NAV of D. What is it? I want to count the number of graphs that have an edge between vertex A and vertex V. That set of graphs is in direct bijection with a set of graphs that do not have an edge here, and I have a degree reduced by 1. That's all, okay? So that is equal to the number of graphs with the reduced degree sequence, okay, that counts all the graphs that have a reduced degree sequence, but then I'm also counting those that have an edge here. So I need to take away NAV in this reduced degree sequence. Okay. Is that clear?
Here the n without the subscript, just the number.
Oh, yeah. And yes, N of D is just the size of G of D. Yes. Okay. And so if I pull this thing out, then this is the N of D minus EA minus EV times 1 minus the probability that I see an edge in the reduced space. So the probability I have an edge if I pick a graph uniformly at random with this reduced degree sequence. Okay? And for these two edge path probability, you have the similar thing. So NAV BV of D is the number of graphs that have degrees that have an edge. Wait, let me double check that I agree with my notes. So in the notes I said BV minus in the reduced one, so minus EA minus EV minus those that have the edge BV. So I'm just doing the whole argument, but like you also have the edge BV. So AV and BV in this reduced degree sequence. Okay, and if I pull out the same number, then this is like N of D minus EA minus EV. So if I divide that number by this number, I get the probability that BV is an edge in D minus EA minus EV, minus if I divide this number of graphs that have both edges divided by all graphs with that edges, that I just get the YAVB of this reduced degree sequence. Okay? A very simple combinatorial trick. Okay. Okay. So now, I mean, you can almost see this one already. So let's do B first, because it's a simpler one. So for B of this recursion, the YAVB of NED, what is this? It's the NAVBV, so all those graphs that have both edges divided by the number of graphs of all of those. And I want to use this So what is that equal to? Well, I want to take out, yes, the NAV of D over the N of D times NAV BV of D over this number. Okay, and now I hope you see this is the probability that I have the edge AV in my original degree sequence. And then for this one, I'm just using that expression, and I divide it by that expression. So this is exactly the PPV of the reduced one minus YAVB of the reduced one over 1 minus PAV of the reduced one. Okay, by observation. Okay, so that one like really follows easily. The other one is a little bit more tricky, but not too tricky. Okay, so for A, we need one more trick. So for A, like let's say you pick your G in G of D uniformly at random. Then what is dV? We start with dV. That's the degree of vertex V in every single graph in the set. So it's the expected degree over G in G of D of the vertex in that graph G. Okay? Does that make sense? Yeah, I mean, it's a deterministic, it's always dV in every single one. So it's the expected degree, but this one you can rewrite as the sum. What's the expected degree, of vertex V and G? Of vertex V, I'm summing over everything that is not vertex V, the probability that I see an edge between B and V. Okay? And now we want to say that that edge probability is equal to that thing. So B not equal to V. That's the number of graphs that have the edge D over the number of all graphs with degree sequence D. And, well, I want to say something about the specific edge probability between A and V. So I write that as the sum over all B not equal to V as the probability of AV of D, which is the number of, let me write an equality and B of D, and I divide it by NAV of D, okay? Because that is NAV of D divided by this N of D. So I'm just pulling out the probability, and that's what I'm left with. Now, what I have to compare is the number of graphs that have degree sequence, that have the edge BV over those that have the edge AV. I mean, we said that's almost our ratio, but it's a ratio with an edge. So I want to remove this edge thing, and that's exactly where I use that observation again. So I want to write this as some number without any edge restriction times 1 minus some probability. So this is again by the observation. Let me pull the PAV of D outside times the sum. And now I have here an N of D minus EB minus EV over N of D minus EA minus EV times 1 minus this probability for that number. So 1 minus PBV of the reduced sequence over reduced sequence BV. And here the probability of the edge AV in the reduced sequence where I remove points from counts from A and V. Okay? And now that here is exactly our ratio, but of a reduced sequence. So that's a ratio, and if you make sure you get the indices right, it's BA of the degree sequence minus EV, and that is just the same thing. So that's exactly what's written here. I have this sum is exactly what's written here. I'm summing over all B's that are not equal to V, this ratio of a slight tiny reduced sequence, and then 1 minus an edge probability of D minus EB minus EV over some 1 minus another edge probability. So yeah, a combinatorial proof and some rearrangements. That's all that it is. Okay, but so how is this helpful? Right, so we have these two recursions. How much time do I have? Okay. I have these recursions, and then I also had the ratio recursion, AB of D, which was dA over dB times 1 minus some bad, I think, AB. Over another bad, and bad was expressed in terms of edge and two-path probabilities. Okay, so, okay, how is this useful? Okay, so what we have seen, we need to start somewhere. We have seen that the PAV of D is big O of D over N. Okay, then if you plug that upper bound into here, you get that this is a 1 plus big O of D over N. This you just forget for now for the simple upper bound. So you get here a product of two probabilities. So it's actually, that's the safe argument to show that Y AVB of anything is big O of D squared over N squared. Well, like we are in our DM or somewhere close. And we have seen that if you plug this into the bad and into the ratio, you get that the ratio RAB of D was dA over dB times 1 plus big O of D over N. Okay. Now I look at this and I apply this recursive formula with all the approximations that I have so far. So apply A, and what you get is that the edge probability of some sequence D, and I'm like not careful with the changing shifts, but I think because of time I'll just give you the rough overview, and tomorrow we'll do it a bit more careful. But you just plug this approximation into the edge probability. What you get is that this is a dV. Let's do this once. Times the sum over all V not equal to B. The ratio of BA in the sequence D minus EV. So that minus EV doesn't change anything about B or A, but I have to be careful with which way around. So that's a dB over dA times 1 plus big O of D over N. And then I have these two probabilities here of a sequence which is a distance 2, but it's also going to be a big O of d over n. So 1 minus or plus big O of d over n, 1 plus big O of d over n to the minus 1. So what is that equal to? It's a dv times dA over the sum of the dBs times 1 plus big O of d over n, which is dA times dV over dN times 1 plus big O of d over n. Okay, so we started with that bound, big O of d over n, and now we have some much better precision of what this edge probability is. It's dA times dV over the total degree. Okay, my relative error is now d over n. Okay, well, and now I can just do the whole thing again. Maybe let's do that tomorrow. So I want to do this calculation one more round with you, so that you get a feeling that these recursions get you closer and closer to something better. And we actually see the formula with the big O of d squared over n squared. So I'll do it formally tomorrow. I'll also say something about the graphicality, so we can feel safe again. And then we do this calculation once, and then we have the ratio. Okay? Yeah, but let's stop here maybe.